Hello, everybody. This is Dr. Ekstrom, and welcome to the third of seven video lectures for this November 1 workshop series. And for the next couple of videos, we're going to focus on how atoms bond together to form compounds. And we have, in this one, we're going to focus on ionic compounds. In the next one, we're going to focus on molecular compounds. And we've already discussed how how most substances are compounds that either break down into molecules or have what we call formula units involving more than one element. What happens is that atoms form chemical bonds with one another to create these structures. Now, a chemical bond, or chemical bonds are forces that hold groups of two or more atoms together and make them function as a unit. So when a compound breaks down into molecules, those molecules are extremely stable. It generally takes some type of chemical reaction with another substance or adding a large amount of heat to get these molecules to break down. And bonds will form if the energy of the aggregated molecule or unit is lower than that of the separated atoms. And really that's, relative energies is really what drives almost all chemistry. Which circumstance, what type of system is going to be more stable? One where we have individual atoms, or one where they're brought together as molecules or as ionic compound formula units. So if we have a molecular compound, the amount of energy required to break these chemical bonds, they're called bond energies, and they're generally very strong. Now, we have a class of compounds that we call ionic compounds that forms when you bring together a metal element and a nonmetal element. These form ionic bonds that are exceptionally stable because of the fact that in order to form these bonds, electrons are actually transferred from one atom to the other. The metal atom will be releasing electrons, and the nonmetal atom will pick those up. So after that occurs, now the atoms have charges. So the metal atom becomes positively charged after it loses electrons, and the nonmetal atoms become negatively charged. Well, now we have these particles with electrostatic forces that are attractive in nature, and they form extremely strong bonds. And even in the case of sodium chloride, table salt seems harmless enough, but if you were to try to make table salt from its constituent elements, make it from sodium, metal, and chlorine gas, it's an extremely vigorous exothermic reaction because of the formations of these ionic bonds. So, and there's a picture of this on the right. During the workshop, I'll show a movie that shows this compound being made, and I highly doubt that there's any middle school experiments where you have students run this reaction. So again, ionic compounds are ones where we have metals and nonmetals together in the same formula. So sodium chloride's table salt, a couple other examples, calcium oxide, aluminum bromide. In each case, we're combining a metal and a nonmetal. Ionic bonds are the strongest of all chemical bonds because of these electrostatic charges. The attractive draw of positive particles to negative ones form extremely strong bonds, and you can see that by the exceptionally high melting and boiling points for these ionic compounds. For example, you have to heat sodium chloride up to 800 degrees to melt it, and over 1400 degrees Celsius to boil it. And so, this would explain why in the distillation example that I talked about in the last video, why nothing happens to the sodium chloride in that process. The water can all be boiled off. The sodium chloride remains stable in the flask because a Bunsen burner flame can't even get up to 800 degrees. So now, you may have noticed that some ionic compounds have different ratios of metal ions to nonmetal ions. I think it was aluminum bromide that had the formula AlBr3. Um, exactly what the formula will be for an ionic compound depends on what metal and nonmetal elements we're working with, and the specific formulas can actually be predicted for many of them simply by knowing what group in the periodic table they come from. So if we look at the periodic table, the metals uh, all come from the left side of the table. They're considered electron poor. Remember that the metals are giving up electrons. And so, for example, a sodium atom will become a +1 charged ion because it's going to give up 1 electron. An aluminum atom, when it becomes an ion, will give up 3 electrons and have a 3+ charge. And so these are all consistent, actually, with groups or columns that they're in the periodic table. With the nonmetal side, what happens is they gain electrons. So they pick up the electrons that the metals give away. And so you can actually predict how many electrons each of these nonmetal atoms will pick up based on what column they are in the periodic table. So you see the pattern. All of the group 7A elements pick up 1 electron, all the 6A elements pick up 2, and all the 5A elements pick up 3. Now, how does this work? Well, the periodic table can actually help explain why this works. The periodic table is designed so that every row represents an atomic energy level or shell. You may remember from the first workshop that atoms, when excited, will emit certain light photons as electrons are dropping from one energy level to another. Well, the periodic table is arranged in having rows that represent each atomic energy level. So when electrons fill atoms, what's represented on the periodic table, the elements on the left are where the electrons start filling. So a lithium atom, for example, will have 1 electron in its outer shell. As you go left to right, more electrons fill in the atoms until you get to the very right, the last group in the periodic table, which is the noble gases. In those elements, electrons fill the entire shell. And so these atoms do not form ions because they have an entirely filled shell without adding any or giving any electrons away. And so that makes them exceptionally stable. And so what's going to happen here? You can ask your students, okay, predict the chemical formula of the ionic compounds that contain the elements, for example, lithium and fluorine. So lithium will give up 1 electron, and that reverts its configuration back to a completely filled shell. Now, fluorine can pick up that electron, and that added electron actually gives the fluorine's outermost shell that completely fills that up. So lithium will generally form +1 ions. Fluorine will form -1 ions. These can go together in a 1-to-1 fashion to make lithium fluoride, LiF formula. Now, magnesium is a group 2 element, and so it has to give up 2 electrons to achieve that completely filled outer shell. Now, the bromine only needs to pick up 1 electron to get a completely filled shell configuration. So what that means then when we bring magnesium and bromine together to make an ionic compound is that one magnesium has a +2 charge, has to be put together with 2 bromides. Each one has a -1 charge. So the formula is going to be MgBr2, and in order to cancel out all the charges, 2 plus canceling out 2 -1s. Last example, cesium and oxygen. I could take it 2 more examples. We have the opposite situation. Cesium is in group 1 and forms a +1 cation. and whereas oxygen forms a -2 ion. And so to bring these together as an ionic compound, we have to have two cesium ions, each with a +1 charge, come together with this single oxygen anion that has a -2 charge. So its formula will be CS2O. The last example is our most complicated one, aluminum and sulfur. Aluminum, as you see, forms 3+ ions. Sulfur forms -2. And so to get these charges to balance, we can't have a 1-to-1 or 1-to-2 ratio with the ions. We actually have to have 2 aluminum ions and 3 sulfide ions. So the 2 aluminum ions have a total positive charge of +6. The 3 sulfide ions have a total negative charge of -6. And so this is the lowest ratio we can put together that cancels out all the charges. So that formula is Al2S3. Now, ionic compounds generally have very rigid and ordered crystalline structures. These ions are attracted together so that they pack together as closely as they can, and every positive ion is completely surrounded by negative ions, and every negative ion is completely surrounded by positive ions. Now, the picture here on the left, this is a called a space filling model. Probably most accurately represents the actual crystal structure picture in terms of the ions will pack together as closely as their sizes will let them. However, in order to study what type of geometries these crystal structures have, we often put together ball and stick models in which we shrink the atom sizes down. You notice we still have differences between the metal ion and the non-metal ion. However, we put in bonds here in this type of model just to see what type of geometries we have. We can see here that every ion has 6 nearest neighbors of ions with the opposite charge. So this is, we have a small purple lithium ion here. Its closest neighbors are 6 fluoride ions equally spaced around it. And we can tell that from the ball and stick structure. It's a little harder to tell that from the space filling model. Finally, it is important to know that an atom size changes significantly when it becomes an ion. If a metal atom loses an electron, its size becomes a lot smaller because the outermost electron shell drops one. Okay, so after the electrons are given away, the completely filled outer shell is one lower than the outermost shell was in the regular atom. So you can see here in this diagram, a lithium atom has a radius of 152 picometers. You pull out that one electron to form a +1 ion, and the radius drops to 60 picometers. Now, with nonmetals, we have the opposite effect. Adding electrons to form ions makes the ion a lot larger than the original atom, and that's because there's more electrons than protons, and so the pull that the nucleus has is not as much on the ion than it is on the electrons in the regular atom. So, for example, fluorine atom has a radius of 72 picometers. Add just one electron to that, and the resulting ion has well, it almost doubles the size. Or the radius. The radius is now 136 picometers after just one electron is added to it. So that explains why here in these models we depict the metal ions as being much smaller than the non-metal ones. And it helps them fit together very nicely. So that's all we have on ionic structures. And so in the next video, we will talk about molecular covalent compounds.